So good evening, everyone, and you're welcome to this section of our analytical methods. And I hope you have been making progress in other courses. And I'm sure the program coordinator must have shared the calendar of the program with all of us. You are aware that your exam may start anytime April, or I think March or April. So you have to inform your lecturers that have not commenced their teaching up to now. You have to reach out to them, make sure that they have started, so that you should be able to take all your courses almost at once. So I don't know whether you have any problem. Thus far, you've covered. God's willing, I may be rounding off my section with you this evening and move over to another course entirely and take off another course, 801. I'll commence my 801 anytime next week. So if you have any question before we commence the topic we have for today, we have experimental design, sorry. We are going to look at a number of issues, then we will conclude. Then you will do your tests, continuous assessment tests, anytime around Saturday, Sunday, this weekend. Or unless I'm not able to upload it, at most on Monday, the test will be available covering your lesson 3 and lesson 4. I will have to start sharing my slide. It's coming. The slide is coming. And some of you have not really logged into these elements for the very first time. So I want to believe that by now, if you have not logged in, means that you're not interested in the program. So we may be forced to delete your name and know the people who are really serious with us. Today, we'll be looking at analysis of variance. Analysis of variance, we'll talk about the introduction, the assumptions. The analysis of variance is based upon, we'll consider key experimental designs. We'll look at the key experimental designs, the completely randomized design, the randomized complete block design. We also will explain all the major experimental designs. We also will explain complete randomized designs. We normally refer to this as one-way classification. We also will explain randomized complete design, the two-way classification. Also, we explain least significant difference. Significant difference is always a method used to separate the means. Please mute yourself if you're not making any comments. We already have a ground rule in this our online training, online lectures, that once you log in, you mute yourself. It's only when you want to make comments, you raise your hands, or you unmute and make reasonable comment. Now, we believe that at the end of this lecture, students will understand the major experimental designs, how you can lay out your experiment, take your data, and be able to analyze it, and also give it interpretation. We also believe that you understand the method of completely randomized design as a key experimental method. fermenter design, or randomized complete block design. Also know how you can use LSD to separate your means. So ANOVA, like the name implies, is analysis of variance in full. Analysis of variance. It stands for an arithmetical procedure of partitioning the total variability. Total variability, for instance, variation in maize height may be due to fertilizer applied, varying soil moisture content, inherent differences among the plant seeds, or even species of different maize plants. So if you consider that as variables and perhaps may have taken some samples, taking some readings from them, so you now be able to consider the total variability and now lump them and now make decisions from them. So this analysis of variance is based on certain assumptions. The error terms are randomly and independently and normally distributed. Randomly, independently, and normally distributed with a mean zero. This is standard assumption in every statistics theory. That's all the errors. The data is randomly distributed and independently distributed and normally distributed with a mean error. So the error is across board, all the variability, all the variables. Now the variance of different samples are homogeneous. They are the same across all the samples we've collected. Whatever variance is not higher in A is not bigger, less in B, and so on and so forth. So it's homogeneous, it's equally distributed. 3, variances and means of different samples are not correlated. These are assumptions upon which ANOVA is based, ANOVA theory is based. So variances and means of different samples are not correlated. That the mean effects are addictive, and sometimes data does not satisfy all these assumptions. So what do? We do what we call transformation. We do what we call transformation in the sense that we can use logarithmic transformation. We can do logarithmic transformation. Use when standard deviation, logarithmic when used when standard deviations are roughly proportional to sample means. If the standard deviations are high, that is the variability in the sample is very, very high, we can transform. Or we can also do square root transformation. All the variables, all the samples, you can transform them using square root or finding the logarithm of those variables. We use this when the rare event of data following Poisson distribution occurs. That is when the variance is equal to the mean for each treatment level. In such a case, the variances must be heterogeneous. So we have few major experimental design. There are quite a number of them, but we're going to restrict ourselves, to just a few. The single factor and also the two-way classification and the one-way classification. Because it's not necessary for us to know all that. There are quite a number of designs, Latin square, split plot, and so on and so forth. We will concentrate on the two, completely randomized design and randomized complete block design. Completely randomized design is referred to as one-way classification, whereas randomized complete block design is referred to two-way classification. We also have Latin square design. We have also split plot design. These are designs used when you have a number of factors and have a number of variables. Depending on those in agriculture will know more, they normally use it. But for us in the environment, we normally concentrate in the use of completely randomized design and the randomized complete block design, as the case may be, or also in combination with other non-parametric methods. Now, the complete randomized design, appropriate, you normally use it when we have one or more factors, but with homogeneous experimental materials. So which means we're only looking at one or more factors. Take, for instance, in a very small area, you are considering the moisture content as it influences plant growth. So within that area, the factor you're considering now becomes soil moisture. It becomes what is a factor. Other factors you feel, and you now regard that particular area as every other factor within that area should be equal and homogeneous. Take, for instance, you may consider maybe temperature effect or soil aggregates and so on. Soil texture should be equal, and no other factor you're considering as you are considering that particular area apart from one, one factor in that area. So that is why it is called randomized complete block design, because that same area is felt to be the variability within that area. The factors within that area is homogeneous within that particular area. The source of variability, apart from experimental error, is the treatment applied. That same treatment, one effect that you're looking at. And it's only appropriate when we have one or more factors, but with homogeneous experimental materials. The source of variability, apart from experimental material, is the treatment applied. So the layout of this CROD, complete randomized design, let us assume that we want to compare.
Gogo said there is 10,000 naira.
Let us assume that we want to compare the degradative capacities of 5 microorganisms on crude oil by estimating microbial load or total residual petroleum hydrocarbon. Take, for instance, we have 4 different microorganisms or 5 different microorganisms. We want to assess their degradative capacity on crude oil. That is the factor, one or more factor. We want to assess how well they can degrade crude oil. Any of them with strength, superior ability, superior enzymes to degrade crude oil. Remember, there could be other factors within the soil where the crude oil is found, factors like the level of nitrogen, the level of moisture, the level of phosphorus, and so on and so forth. Now, we are assuming that all these other factors are equal. They do not vary. The concentration of nitrogen is the same across all the units, across all the areas within that crude oil contaminated field. What we are interested in, we are introducing 5 different microorganisms to test how each of these organisms will perform. Which of them has superior ability to degrade this crude oil? Now, how do we assess it? Is either that we will look at the total residual microorganism, or we can also harvest the growth of microorganisms. Either way, we should be able to have an idea of the microorganisms that have really done well. Remember, these microorganisms may be functioning in different experimental units, or maybe we put them, arrange them in pots, in small petri dishes or in pots, and now assess how they grow. For some of them, they may not have that capacity, that right enzymes, they may not really grow. Remember, the idea is for the microorganism to assess the carbon present in the hydrocarbon and utilize it as substrate. If they don't have the right constitution of enzymes, they won't be able to do that. It's only the microorganisms with the right constitution of micro enzymes will be able to degrade it and now proliferate and grow. So with that, if the microorganisms proliferate higher, it then means they are actually utilizing the crude oil. So you can translate it to mean that they are doing very well. Or otherwise, you can also measure the other way around. You can also measure the residual petroleum hydrocarbon in that particular unit. Take, for instance, we fill this experimental unit with equal concentration of crude oil. So the unit that are low in concentration, maybe after 4 months or 5 months, of course, the microorganism may have utilized them. The ones that are still retaining the crude oil is still high, concentration is still high. Of course, that microorganisms may not have fed well in that particular compartment. So this is a little background on the type of experiment we are looking in as one example we are going to use to fit into this CROD. If there is no cause to suspect that various parts of the land area involved differ in nutrient and water content, concentration of crude oil, and pH. So we consider the treatment as what? The microorganisms, okay? Now, the microorganisms will normally replicate each of these treatments. We replicate each of the treatments by having four replicate units, experimental units. For each treatment, for each microorganisms, we replicate it 4 times. For each microorganisms, we replicate it 4 times. At the end of the day, we'll have a total of 20 experimental units or 20 plots where we are going to observe the growth of the microorganisms, or we consider to measure the residual concentration of petroleum hydrocarbon. Now, this is the layout. Consider all these A, B, C, A to be the microbes. The microbes, we have A microbe, B, C, D microbe, and we have randomized it within this unit, experimental unit or plot, as the case may be. Consider this to be field or experimental plots. So we have to randomize all these plots. Okay, we need to have to randomize them and consider this A. If you look at this, we have A1, A2, A3, and A4. This is one replicate 1, this is replicate 2, this is replicate 3, this is replicate 4. For each of these treatments will occur 4 times within this experimental unit. So I believe you is clear to you. So the basic assumption here is that all the 20 plots or pots are alike, and they have effects from left, from the north, from the west, from the south, all are randomized. It does not matter where any of the treatment falls. Remember, if you're checking from replicate A, replicate 1, A, B, all the treatments are represented. Replicate 2, all the treatments are all represented. Replicate 3, all the treatments are all represented. So this particular layout is referred to as completely randomized design. Now, the second stage is to construct our hypothesis. In this case, we have our null hypothesis to say that all the microorganisms have the same degradative capacity. They have the same degradative capacity. The microorganisms do not differ in their degradative capacities. They are the same. A is not superior to B, B is not superior to C, C is not superior to D, D is not superior to E. Then for the alternative hypothesis, at least one of the pairs of these microorganisms differ. That's what it means, that at least these organisms, one should be superior than the other. But the one that is superior, we do not know. Okay, we will know at the end of the experiment. So at least one of these pairs of microorganisms differ. Then we have a model that goes with this CRD. The analysis is based on the model. This model Xij equals mu plus T treatment I plus error Ij, where Xij is equal to value of observation, mu is unknown constant, then of population being common to all the treatments, Ti is equal to treatment effect, Eij is equal to error term. So it's only treatment. Like I said, treatment is only variability that is considered in CROD. Now, at the end of the field trial or pot experiment or bench experiment, we're able to come up with this result. So now we are looking at the concentration of petroleum hydrocarbon. Now, in replicate 1, the microorganism, this is the way they are fed. We have 2 residual of 2 parts per million of petroleum hydrocarbon. This is 3, this is 4, this is 5, 3, 6, and so on and so forth. Perhaps the initial concentration that went into this experiment may be 15 or maybe 18 parts per million across all the pots. So at the end of the day, we have this particular response from all these microorganisms. So we will know the microorganisms with higher degradative ability at the end of the day. Now we need to get the total and the mean values of each of these microorganisms, the way they performed in each of the experimental units. So we have the mean of microorganisms A to be 3.5, mean of microorganisms B to be 4.5, C, and so on and so forth. Now, we need to calculate our sum of squares, the variances. Total variances sum of squares is equal to the treatment sum of square plus the error sum of square. Please take note of this particular equation. This is from where we will move on. We have, before we do that, we also have to calculate the correction factor. The correction factor is the summation of all these values, grand total of the values. If we put all the total here, calculate all of them, the total, it will give you 115. If you can work it out, what you're going to get here is 115. Now, this 115 square of 115 all over the total number of observations. Total number of observations is 20. This is the total experimental unit over 20. It will give you, if you divide it correctly, you'll get 661.25. So this is the correction factor. Remember this correction factor, you're going to use it to subtract whatever values you're going to obtain from total, from treatment, and from error sum of squares. Now, the total sum of square is a square of each of the observations, square of each, 2 squared, 3 squared, 2 squared plus 3 squared, 7 plus 7 squared plus 1 squared, from 10 till the last value, 12 squared. So that will give you the total sum of square, then minus the correction factor. If you work out that correctly, you're going to get 895 as the total minus the correction factor. You're going to get 233.75. Okay, now take the following steps for treatment sum of squares. Square each treatment total. Square each treatment total. The treatment total, let's look at the treatment total. Treatment total, we have 14, we have 18, we have 34, we have 7. So 14 squared over 1, 2, 3, 4 over the number of observations. 18 squared over number of observations over 4. 34 squared over 4 number of observations. That is why divide each square total by the number of observations added to obtain it. Add all the recipients. So that's why we have here 14 squared over 4 plus 18 squared over 4 plus 34 squared over 4 plus 7 squared over 4 plus 42 squared minus the correction factor. If you have done that, we are going to get 211 as treatment sum of square. Now, the error sum of square, since we have obtained total sum of square and have also obtained treatment sum of square, if we make error sum of square the subject, like you can find here, we should be able to seamlessly obtain our error sum of square. Very simple. We make error sum of square the subject of the formula and substitute values we had already obtained on total sum of square and treatment sum of square. If we've done that correctly, we will get 22.75 as error sum of square. With that, we have all obtained all the variances for the treatment, for the total sum of square, and the error sum of square. Now, we have to obtain the degree of freedom for the CRED design. The source of variation, we have total, we have treatment, and error. Total sum of degree of freedom for total, we have the replicate times the treatment minus 1. Remember, we have replicate 4, treatment 5. So it's 20 minus 1. We have 19 as the total sum of square, as the total degree of freedom. Treatment degree of freedom, number of treatment is 5 minus 1, that is 4. Error, we have to substitute this model treatment into replicate minus 1. So 5 times 3 will give us 5 times 3 will give us 15. However, if you minus 19, 19 minus this is treatment 5 minus 1, that is 4. 19 minus, we will get 15. 19 minus 4 will give you 15. So we have replicate, we have treatment. Now we have to construct our analysis of variance table. It's very sacrosanct. It has this column 1, 2, 3, 4, 5, 6, 6 columns. So we will now substitute the values we have already obtained. For the source of variation, we have total, treatment, and error. Degree of freedom for total, of course, you know how we got it to be 19. For treatment, 4, and the error, 15. Now, sum of square, I've already worked out this. 2, 3, 3 will substitute to obtain this, complete this table. For the mean square total sum of square, this is off, is no longer relevant to get us to the hypothesis. Now we have 4 divided by the sum of square. 211 over 4 will give us 52.75. Also, we divide 15 by the sum of square. 22.7 will have 1.52. To get our F calculated, to get our F calculated, we have to divide 52.7 over the error mean square. If we have that, we have our calculated F calculated to be 34.7. Remember, the standard practice, this particular experiment is carried out having the critical significant level, the critical F alpha value critical level to be 5%, 0.05. So we'll now go into the table, F table, to find out the F tabulated. Now I will share the screen for the F distribution table so that we can obtain how we obtain our F table. Our F table is we will check our F table from the error degree of freedom by the value from the critical value that we have, F degree of freedom plus the treatment degree of freedom, error degree of freedom plus under 15. We have 4, the degree of freedom for treatment and the error degree of freedom. We have it here, the degree of freedom for treatment and degree of freedom for error. We'll check it, we'll get the F calculated value. F calculated value is 3.06. Yes, let me remove share. Let me exit this and now upload. Let me see if I can get the F distribution table. Wait, the table is being uploaded. Now, we have 4, 14, 3 point. Okay, this is, remember we're checking it under 0.05. 0.05, we have 15, 14, 4 under 15, 15 under 4. Remember the F value, we are not checking it at 0.01. We are looking at it at 5%. Alpha equals to 0.05. So we have 15 under 4. Are you seeing it? Is it clearer now?
No, sir, we are not seeing it at all.
You are not seeing it. Is it clearer now?
Yes, it's clear, sir. It's clear.
It's clear.
It's clear. I'm seeing.
So we have the treatment, the error degree of freedom is what? 15 under treatment degree of freedom. So we have is F distribution table not shared? Are you not seeing the F distribution table in your screen?
Yes, we can't see it. I can't see it from my side.
I can see it.
you have a poor network in your area. It's uploaded. It's very clear. We have, okay, let me enlarge it a bit again. We have from the vertical line, you check the error at the vertical axis. This is 15. For the horizontal, you check the treatment, which is 4. If you go down where they meet, where there is intercept, you have 3.06. We regard this as the tabulated F value. Remember, we have our F calculated value. This is the tabulated F value. So we are going to exit this. We are going to exit this, and now let's go back to our slide. Now, if all the procedure for the calculation is there, we now have the mean square value estimate of variance, the sum of square divided by the degree of freedom, and therefore F calculated for the treatment effect. We also have the F calculated treatment over the error mean square. If you do that, you get 37.7. Now, there is a standard rule, the decision rule. If F calculated is greater than what F tabulated, what do? You reject the null hypothesis. That is the standard statistical rule. Once you have your calculated calculated F value is greater than the tabulated F value, you reject the null hypothesis with 5% probability of type 1 error and conclude that at least 2 of the microorganisms differ in their degradative capacities. If I take you back to the hypothesis in the earlier slide, let me quickly go back to the hypothesis limitation. Why is the handling? Victor Wadima, please mute yourself. Somebody should call Victor. Okay, good. If you look at this hypothesis, remember we said for the null hypothesis that the ability of these 5 microorganisms are equal. They don't have different degradative capacities. Then for the alternative, we said at least one pair, A and B, B and C, C and D, D and E. At least one pair must differ. Now we have conducted the experiment. We have taken a decision because of our F calculated is greater than our F tabulated. We therefore strike off the null hypothesis. At least 2 pair of these 2 microorganisms at least differ. They have a superior ability to degrade the microorganism. But there is something we must note. Assuming that we are deciding on the null hypothesis means that all of them are equal. We will not do any operation in this. But since we said 2 pairs, at least 2 pairs of at least 2 of the microorganisms differ in their degradative capacities, we have to go extra mile to know the microorganisms that actually differ. Okay, so let's make progress in this our study. Now, the key advantage of completely randomized design is one, very simple to classify. If you look at the model is straightforward and it's easier to design. Look at the way we laid it out. You get our microorganisms and we consider only the factor of the microorganisms. We have not considered other ones. A time will come when we consider effect of moisture, effect of nutrients in that same experiment. Maybe we'll add amendment to it. We may not have or add moisture to the experimental unit. These are all factors, but rather we have choose only one, the microorganisms. So this CRD is very simple and very easy to lay out, allows for a maximum degree of freedom for estimating experimental error. Data can still be easily analyzed. Look at the way we quickly analyze the data now. It places no limitation on the number of replications. We can decide to replicate one treatment over having 20 replicates in one treatment. It doesn't really matter in CROD. Now, the key disadvantage is that it is used when the experimental material is homogeneous, which in real situation you may not really find. It's all like concluding that that experimental unit, how many now? 20 of them, that they have equal nutrients, assuming that all of the 20 experimental units have equal nitrogen content in all of them, or their moisture content are all equal. That is, you may not be such condition in science. It's just bogus, very bogus assumption, which may not be real, you know. So such a condition is not common in real life. So, but we need to assume it so that we make progress. Now, suitable only for a limited or small number of treatment. If you increase the number of treatment, of course, and increase the number of treatment and the number of the size and the number of plots we expand. If that is the case, there's no way anybody can trust that homogeneity will be lost completely. So that is why it only allows for a small handful of treatment for you to use the CROD. So it's a very small scale experiment for undergraduate and perhaps for a master's degree, you know, that will not really demand, you know, number of factors in the experiments or treatments that will bring about very large expanse of land to carry out the experiment. Now, I want us to look at, let me expand this, I think it's possible. Let's quickly look at randomized complete block design before we will move over to looking at how we can separate the means, since it's significant. Let's quickly look at what randomized complete block design is all about. Here is like it's an advancement on the CROD. It's an advancement on the completely randomized block. This randomized complete block design is telling you that that variability we assume to be homogeneous may not really be. Here, variability other than treatment error and experimental error could be identified. Let us consider a field in this figure 1, in such a field sloping down from T, this is T, to Z. I think, let me see if I can, okay. From T to Z, assuming that this slope, this is an area, a landscape is floating in this direction. If you're considering moisture, if you're considering drainage pattern, water moisture, there's no way you will consider this area and this area to be the same, even in soil aggregate and types of planting or plant species and so on and so forth. There's no way the type of plant growing inhabiting this zone will be the same in this in the lower zone, and also even the nutrients and so on and so forth, they cannot be equal. So cannot be equal. So we have to partition them and now consider each of the treatments in blocks. Each of the sections, we consider them as blocks, represents a replication. So every treatment must be given the chance to appear in each block to avoid bias. So if we now consider the earlier experiment we carried out, especially if this place is our pot or plot. So each of these units, we consider them to be replicates. We have 1, 2, 3, 4 replicate, 1, 2, 3, 4 replicate, and so on and so forth. So each of these we are using 4 microorganisms here, as the case may be. We have A, B, C, D as against, in no particular order anyway, as against the first experiment. It doesn't really matter. Represents a replication. So every treatment must be given the chance to appear in each block to avoid bias. So we have 4 treatments and 4 blocks. Now we have the hypothesis for this experiment. All the treatment effect is equal to 0, means they are the same. The alternative hypothesis said the treatment effect is not equal to 0, means at least the treatment varies. Effect, at least 2 pairs differs. Now, we also will say that for the block hypothesis, now we are introducing blocking. Another factor apart from treatment, another factor which could be maybe nitrogen content in those plots is not what the same. At least each of the plots should not have the same nutrient content. We say, okay, the blocking effect is equal to 0. You're considering that the nutrients are all the same. Alternative hypothesis is saying that the blocking at least is not the same. The blocking, one particular block may have higher nutrients than the other. So the linear equation is xi, which is the total variability, equal to the population constants common to all the treatments, the block, and the error. Now, this is the treatment layout, the result obtained during the analysis. So we consider the result we obtained in the first experiment and the block total. So in this case, remember during the sorry, let me remove this. Now, during the CRD, we only consider the treatment total, where we got 14, 18, 34, 7, 14, and got their mean values. For the blocks, remember we have 4 replicates. We have them, all the values we got across all the replicates. We have 23, we have 28, 29, 35, and also our grand total is still 115. Now we also do our usual computation. We have the total sum of square. In CRD, we only had total sum of square for treatment and error. Now we have introduced blocking. So we have total sum of square, the treatment sum of square, and the block sum of square, and the error sum of square. What is new here is only the block sum of square. Block sum of square, what do? We still have to do square of 23 over the number of variables that made up 23. We have 1, 2, 3, 4, 5 as against the treatment total. So 23 squared all over 5, 28 squared all over 5, 29 squared all over 5, 35 squared all over 5. That will give us our block sum of square. Remember, the same process we use in the CRD to get both the correction factor. Already we have worked out the correction factor, this one, to be 233.75. You get the total sum of square and minus the the correction factor. The process is the same. It has not changed. The process to obtain the treatment sum of square is still the same. It has not changed, still the same value. Where we have now is the blocking, where we now take the replicates, get the square of the total all over the number of observations that made up the total. So, and now minus CF. CF the correction factor, and we obtain 14.55. In the same manner, since we have obtained the correction, we can also make error sum or square, the subject of the formula, and now obtain the error. Find out that the error has actually what? Reduced, because we have introduced blocking. So which means blocking actually had effect. We have reduced the error value to 8.2. So let's make progress. In the same way, we do our degree of freedom. We also have our degree of freedom. The block degree of freedom, remember the block is equal to the number of replicates. Number of replicates is 4, 4 minus 1 is 3. The treatment is treatment minus 1. Then error, we have the replicate minus 1 into treatment minus 1. So we have the replicate 4 here, replicate for 3 times 4, which means is 12. So once the error square has also reduced to 12 instead of 15. So we have the total 19, the block 3, and the treatment 4. Now we have already obtained our sum of square. We have our block, we have our treatment. So we are interested in treatment and block to see how significant they are. So the same way, we divide 14.55 by 3 and also 211 by 4. We have this and that. We have for block, we have 4.85. For treatment, we have 5.275. Again, we'll have to divide the block mean square by the error. Please take note, by the error, and also divide the treatment mean square by the error. If we do that, we'll have our calculated 7.13. If we divide 4.85 by 0.68 and 52.75 by 0.65, we are going to obtain this F calculated, the values of F calculated. And if you compare all these values, you find out that they are all greater than the F tabulated. We're going to look at it in that case, which means that blocking has effect. The treatment also has what? Effect in this matter. Now, the decision rule for treatment, since F calculated is greater than T tabulated, we reject the null hypothesis and conclude that at least 2 of the microorganisms differ. We took this decision earlier, even when we use CRD design. But in this case, for block design, for the blocking, since F calculated is greater than F, but we reject the null hypothesis and conclude that at least one of the soils would differ. In one way or the other, it could be that plot A replicates A, 2, or 3. At least one of them has higher, depending on the factor we are considering. Here we are looking at nutrient, may have higher nutrient content than the other. Now, one advantage of using ROCBD is that when blocking is effective, ROCBD increases what? Precision. Increases precision. You can rely on the experiment, since we rarely have heterogeneous experimental material. Of course, this has shown clearly that CRD did not give us a good design, because there's no way we'll assume that those pots have the same nutritional content. They differ, but we never considered it. But now we have introduced blocking. It has obviously shown that what the nutrients in those pots differ. Now, that is one advantage. It also allows the use of any number of treatments and replications within the limits of the experimental material, unlike this other one that you may, if you increase it, it requires a very large area. It allows the use of any number of treatment and replication within the limits of the experimental material. Like in CRO, the missing data can be handled easily. Analysis is relatively easy. Block means can be used to estimate block effect. This may increase the scope of inference. Like we have already considered the block to mean the nutrient. You can consider it to give it any value or any parameter, so to say. It could be the pH level of that soil, may differ. Call it any name. Of course, it has added value to the result, to the inference from this experiment. So it increases the scope of decision, the scope of inference, things you're going to come out with at the end of the day in this experiment. Now, disadvantages of RCPD. Key disadvantage of CRO is usually suitable for a limited number of treatments. Limited number, because the number of treatments must be the same with the number of what they block. With a large number of treatments, a block may no longer be homogeneous. Variability with the block should be less than that between blocks. So that means there is no variability again. The block, since we are blocking, we will consider that block A should be different from block B, and block B should be different from block C, as so on and so forth. So variability with the block should be less than that between blocks. So if you increase the number of blocks, it may not, the variability may be lost completely. Now, that takes us to a situation where now we have found out that both block and the treatment are all significant. So which means we must carry out another operation to know the means that are superior and the means that are not superior. We have to rank the means and group them. Some are maybe that one is higher than the other one does not mean that they are different. So this is pairwise comparison enables us to group these means, know the one that are superior and know the one that are less superior, and kind of ranking. This pairwise comparison helps us what? To rank only the significant means. Okay. Now, the F-test for any testable effect in the analysis of variance table may indicate significant difference. In this case, this test has indicated significant what? Different, has effect, because we have not chosen the null hypothesis. We have chosen in these two operations, we have chosen the alternative hypothesis. That means there is effect. Okay, there is effect. If there is no effect, there is no way, there is no point comparing the means. We would have ended that. There is no need. Means once the test shows non-significant, there is no point comparing the means. We consider them to be one, the same group. So when significant, it suggests that at least one pair of the means in question must be different. So the F-test indicated the significance in these present examples. Statistical difference implies that whatever difference can be referring to is too big to be attributed to experimental error. So it's real. It is really not a chance event. So, however, the F-test did not tell us which means actually differed. We have to set up a criterion of measurement to find out how different a difference must be before it is statistically significant. I'm sure we are not hearing this for the first time. We have examples of models that can be used to carry out that operation. For experiment containing meaningful built-in comparison, the generally accepted procedure is that of computing the single degree of freedom mean square variance to the meaningful individual contrast. So we have example, this significant difference, Duncan's modification of LSD, for Bayesian modification of LSD, Turkey's honest significant distribution, and student human core test. So these are all examples, but we have been consistent using this significant difference, that's LSD. And I recommend that we will be consistent be using this LSD. the way we are going to do this, we are going to show it now. However, in the recent time, statistical packages have been, handy to carry out all these functions. If you have sufficient time, even though that there are statistical packages that can run this, but for us, we will have to doing it manual for the sake of these analytical methods. For the sake of this course, we have to learn it manual. But if you privy to learn any of the packages, statistical packages, you will have to run this thing seamlessly. Now, we have the LSD. LSD, least significant difference we mentioned earlier. The LSD was formulated and later modified. Please, whoever that is disturbing, please mute yourself. Call that person to order. We're in a classroom. And later modified by R.A. Fisher. It must be used only when F-test indicates significance. And that's when you have accepted the alternative hypothesis. Please, you should know that that's why I have placed it in uppercase letter. It's only when you use it, only when you have rejected the null hypothesis and accepted the alternative hypothesis. Now, from the RCBD ANOVA table, treatment means, of course, we have A to be 3.50, B 4.5, C 8.5, D 1.75, and E 10.5. These are the values of microorganisms, concentrations of in those units, or concentration of microorganisms, or the residual petroleum hydrocarbon in these units, as the case may be, depending on how you want to consider it. Now, the difference between A and B 3.504 is what is 1, and B and C is 4, and C and D is 6.75, so on and so forth. In a difference of 1 enough, is a difference of 1 enough for us to declare A and B different? That is the issue. What is the benchmark? What is the least difference that we will now get and say that actually A is different from B? That is what we want to do now with LAZ. That's what LAZ will help us to do. What is the benchmark? What is the least value that we'll consider if we minus A and B? If it's within that value, if it's less than that value, you consider it not different. But if it's more, you consider it what? Different. That is what LAZ will help us to do. That's what we want to do now. Now, we must know what is the least value to expect before we declare any different what? Different. Now, the formula for LAZ is equals to T. Remember, you're comparing two means, and that's why you're using the T table. Of course, alpha over 2, because you don't know, it can be left, it can be right. So that's why you divide the alpha by what? 2. You will consider the error degree of freedom. Error degree of freedom for this blockchain is 12. And we have our square, the variance square, error mean square, 2 times S square all over the number of replicates. We have our alpha equal to significant level, the mean square error. Error mean square, this error mean square, then number of observations per treatment total, that is replicates. Replication, the alpha is 5%. The procedure, we have to get all the values and substitute it here and get our least significant difference. So of course, error degree of freedom, we have already considered, we have already gotten it to be 12 in the randomized RCBD design. Now, T 0.02, if you divide alpha 0.05% by 2, you're going to get 0.025 plus the error degree of freedom. If you get this value under 12, what you're going to get is 2.179. Now, we already have 2.79. This has been obtained. Then we'll substitute 2 into 0.68. 0.68 is error mean square. Let's go back to that. You get it error mean square. Error mean square is 0.68. The error mean square is 0.68. You obtain it here. This is where you get it. Then let's go back and substitute. I just want to take you back there so that you understand how we got this. And number of replicates, of course, is 4. By the time you resolve this, you're going to get LSD to be 1.27. That is the least value. Now, if you minus A and B, of course, A and B is 1, which means they are the same because it's less than 1.27. If you minus B and C, what are you going to get in this? We said B, A and B is 1, B and C is 4, which means B and C, that is what? Difference. So, and the second one is 6, which means they are above 1.28. Now, let's look at it. Now, let us now find out the mean that differ, knowing that the difference must be at least 1.27. Step 1, arrange the means in a descending order, omitting the lowest horizontal, and in an increasing order vertically, omitting the highest. Of course, you can manually do this. Okay, subtract the vertically from horizontal, line up the means in a decreasing order, and do the comparison with LSD 1.27. You can as well, if you do it comparing them. Okay, of course, this is the mean in decreasing order. This is the mean in increasing order. Look at the increasing order and the decreasing order. If you subtract this one, if you subtract, if you subtract 10 minus 1.7, of course, this is what? This is 8.5. That is difference. If you subtract D over 6 points, this, you find out that there is difference, and so on and so forth. So you have these values. You have these differences, as the case may be. So if you get the differences, we will now arrange them. Now we can give letter A to the biggest mean, B to the next, and so on and so forth. So this now is A. If you group them, of course, let's look at excuse me, just a minute. Let me pick a call. I'm coming. Sorry, actually an important call came. Can you hear me now? Hello, can you hear me?
Yes, we can hear you.
Yes,
Yes,
we can
yes,
hear
we can
you.
hear you.
Yes.
Now, let's go back
Yes, we can hear
to
you.
the means that we obtain. Where do we get that mean easily now? We have A. We have the means. In this one is in increasing order. This is decreasing order. Let's go back to the table that we have the mean so that you can refresh your mind. Now we have the mean. A is 3.5, B is 4.5, C is 8.5, D is 1.5. If you look at all these means, you find out that 10.5 is the superior, is higher in number, followed by which other one? C, followed by B, followed by A. So we want to rank these means and know the one that are not different. And if you minus A and B, you have a value. You have a value that is 1. So obviously A and B, there is no difference between them. They are equal, even though that 4.5 is greater than 3.5. We regard them as in the same group. These two microorganisms belong together. They have equal strength, but E has higher strength than all of them, followed by what? C, followed by B. Okay, so that is how it's ranked. Now let's go back to that the last this thing we have. Now we now said A is the highest value, B is followed by B, but 45 and 3.5, that's A and B, they are the same in terms of force strength. Much as they are the same, they are even higher. They're also higher than 1.75, which is D. So this is the ranking in terms of grouping. We call it group. You can, if you approach some articles, published articles, you've seen that the mean values are ranked A, B, C, D. Remember, this ranking is done on 5% probability level. It's ranked based on 5% probability level. So this is the how the microorganisms fare in terms of their ability to degrade the petroleum hydrocarbon. Okay. Now we'll end it here. If you have any question, you ask. I've taken it lightly so that you'll be able to follow. For the two designs, the completely randomized design and the completely block design. One is one-way classification, two is the two-way classification, where we have considered two factors. We considered the type of microorganism and also blocking. So if you have any question as regards the layout of these two experimental designs, you ask.
What? If I slap you, you continue what you're doing now. When they make this everything.
So I also encourage you to read through this material over and over. You should be able to understand it. You should be able to understand it. If you have question at any point, you ask, and we will. The quiz will be available by Sunday or Monday. I'm not really sure when I will be able to upload the quiz. There's about 10 or 20 quiz questions that you have to answer. So if you have any question, you ask. No response at all. Everywhere is dead.
So no questions.
So you mean you understood the layout, you understood the way you work out the variances, the total variances, the treatment variances, and the error variances. and be able
I
to
don't
construct
know.
the
You don't
ANOVA table.
understand, though.
We don't
Learn how to
understand though. The
construct the
thing is
ANOVA.
We
flying.
we don't understand, but I think we were going to read about the quiz.
You read it. Going through it again means
The,
punishing me. Means
the
you're giving
quiz
me
book.
double, giving me punishment, and also
No,
hitting on
sir.
my data.
No, sir. We wouldn't want you to go through it again. We'll read the material. And if there is any
Yeah, the material is quite
consent, we'll let you know.
self-explanatory. I've been able to, because it's online, I'm not writing anything on the board. I've been able to simplify every procedure. I've been able to define all the procedures. And we can pick any statistical textbook.
We'll do that, sir.
Randomized complete block design is an age-long model that you use for any common experiment. Okay, it's used for any common experiment. Even if you consider two-way classification, randomized complete block design to be complex, but you should be able to understand how to use CROD to carry out your simple experiment. Whether you're doing what is it called, water analysis, you're interested in determining the water quality, you are determining air quality, you will subject them to simple CROD design or even complete randomized block design. Take, for instance, you are working on a Otamiri River. You want to consider the impact of perhaps waste dump or impact of effluent discharge within you divide the river in compartments, upstream, downstream. These are blocks. The upstream, what happens in upstream, what happens in downstream, what happens in midstream. These are blocked. You have blocked it. You take data here, you take data here, you take data here, and also determine the parameters and subject them, lay it out in this particular data and take the data and know the difference between what happens in this upstream, know what happens in the downstream, and also the parameters as well. So for any particular experiment, you will always subject it to any of these experimental designs and be able to put it in any of this statistical package and analyze it and define and be able to interpret the result. That is how it's done. Provided you know how you do your sampling, how do you lay out your experiment and be able to take your data. Remember I said, you don't just go to the field and begin to take your data. You must plan the way you lay it out and collect the data. That is only when you'll be able to run the analysis and get proper results and be able to publish the results. Is that okay?
Yes, sir. Thank you for the explanations.
Yeah, that
Yes,
is how
sir.
it. I will encourage encourage your friends, those that have not logged in. The number is still low. 39 in today's lecture means that it's a far cry. We gave 76, and this is a compulsory course. We gave 76 opportunity to study, and this is 38. Last time was 40 or thereabout. So we've not even hit the mark. So which means a good number are not continuing with the program. That is the implication. So however, we have taken, how many? I've taken one test. This second one will be a deciding test to know the people who are, and that's why I'm not uploading it right away. I want to give people today, tomorrow, you read the material. You read the material. The standard practice would have been to upload the quiz now, but that would be bad. So you use today, use tomorrow, perhaps use Sunday. By Monday, the quiz will be available and you do it and pass. So like a good number of you did very well. Some got 75, over 75, 70, 50, 45. The list, the minimum, the pass mark is 45. Just 2 or 3 persons got below 45. That is quite encouraging. I commend every one of you for doing well in that first quiz. So same will be this second quiz. You do it. Okay, I encourage all of you to do it. And if you don't have any other question, there is no point, wasting our data. Or if you have comments, any problem concerning the program generally,
Yes, sir.
so express your feelings. Let me know.
Yes, sir. My name is
Go
Victor.
ahead. Okay.
Sir, it's regarding the first test we did. Honestly, personally for me, and I know there are some other of our colleagues that were still commenting on our group chats. We missed the test. When I was trying to, I couldn't finish on time, and I reached out.
Okay, do this one. Do this one. That's why we have multiple tests. Don't bother. Don't. You still have another chance. There's a test coming up on Monday. Don't make sure that you correct all the errors and all the problems. Prepare now and be waiting for it. You have all the information you need. I say
sir.
Sunday, Monday. In fact, I normally give over, if I upload it on Monday, that I will give at least 6 hours notice or 8 hours notice, as the case may be. So some of you complaining, you shouldn't complain. Let's not behave as if we are in nursery and primary school. We are all, some of us are big time parents. So that thing your child will do, you flog him or her. So don't do it. Some of you are not, you're just, indifferent about anything. Don't take things serious. That is the situation. I can't tell me, I announced about the test. I gave time and everything, and say people are complaining. It's wrong. That's not the way to go. You know what I'm talking about. That's not the way to go, and we shouldn't continue. So, any other question so that I can run away and do other things?
No, sir. Thank you for your time.
Thank you, sir.
I will. All right. You're welcome.